I think not. For this question, I'll upload it today on the EE class. If I haven't, I'll check it. So right, we are done with this kind of protocols, and this is interesting. But a small subject that we never even discuss it fairly is the usage of public key infrastructure or the management. How somebody can publish public key and a private, keep the private key and publish the public key or verification key to the other users. We always said that we have a database that people would put their public keys there, but the problem is like everybody can go and say I'm Alice, in the public directory or a database, and insert those keys into that infrastructure. So then some attack can start to initiate even from there. So we said that we would want to have some certificate authorities. These are some agencies, some entities that are available on the internet. They would facilitate this entire process of verifying somebody's key, authenticating somebody, and also inserting somebody's public key into the DB. But it is a little bit different than the idea that you have from the database, because if this is just a simple database, then everybody can edit the database, and then therefore they would be able to replace somebody's public key. So when we are talking about putting somebody's public key into a repository, then we always talk about certificates. So every user, instead of just sharing the public key to a database, inserting it to a publicly available database, we will talk about having somebody is got a certificate. So let's discuss with the Alice certificate. So this is the certificate for Alice. And then if you look into the certificate, it starts to say the certificate is for Alice. This is the public key of Alice. This is the verification key of Alice, right? She has also a digital signature. And then they start to have some more information. For example, the start time and then end time. A start time and an end time is referred to the time from when the certificate is valid and the time that it expires. So we would put those things. And honestly, a lot more information. This is not really the case in our lecture today, but there would be a lot more different information in a certificate, but these are the most important one that matters for us right now. So we have these things, and we can't just put this information on some public database because people would be able to go ahead and change it. So what we do is that we use a certificate authority. Certificate authority, imagine, is an agency that runs that repository that or records in a database. So this guy himself has a certificate X, and it is known to everyone about that his certificate is valid. So what it does is that he will compute a hash of this entire things, right? So this would be apply a hash function. So the result would be hash of A. And then what he would do is he would go and sign this entire information at the end of the certificate. So the sigma equals to sign using the signature key of X, this hash A, right? And then this thing would be the last thing that you attach to a certificate. So far we've learned that everybody has a certificate. Certificate has some information, and then we have some other authority, somebody's else certificate, which is like signing key X. This guy would sign this information and attach the signature to the end. Right now, after we have signed this information and attach it to the end of the certificate, you can basically share the certificate without any protection to anyone. And the reason for that is because if you change any bit of information over here, then the signature wouldn't verify anymore, right? So by idea of using using signatures to protect the certificate is such a good idea. As long as we can take care of some problems that we would come and we would discuss about it. But you don't need to have definitely a database. You can imagine that this could be a text file format. You can share this file with somebody else, and at the end they can verify the signature using the verification key of X, and then and then they would be done, and then they can basically make sure that the certificate is indeed for Alice. But the problem that we are going to discuss now is something that is known for for certificate chain, and the question that how can you trust, or where do you get this verification key for this certificate authority X, or how can you trust this guy in the first place? So this would be the thing that we want to have a small discussion about it. So everything starts on the root. We have this certificate authorities, and they are, they could be intermediate ones. So let's just start with something we call certificate authority Z. So everything begins from here. This is the beginning of a tree. And then we have the certificate authority Z, and this guy would go ahead and certificate authority Y, sign a certificate for another guy, and this guy would also create a certificate and sign it for some other CA X. Then this users, we have Alice, we have Bob, they they get a certificate, and then in their certificate it says that this is the signature key for Alice, verification key for Alice, signature key for Bob, verification key for Bob, and these things are signed with certificate X. This notation means signed or verified. All right, so some certificate authority, sometimes this one to be Google, for example, or VeriSign on the internet. These are the agency certificate authorities that they are able to, you pay them, they will sign a certificate for you. So we would use this certificate to to sign them. So the question that you can have is that, well, somebody, certificate authority X, says that I signed this, guys. Okay, the verification under the certificate over here based on this X is verified. Then the question is that how can I verify this X itself? Who is this X? Even though verification works, who's this guy? So if you look into the internet, this is not easy that you suddenly would be able to verify this X. There is always a chain of certificates, and those over here we call them normally intermediate. Intermediate CAs, the Y is the intermediate one. So this is how it works. X has a certificate itself. Let's call that one certificate of X, which is signed by certificate of Y. So this guy has S of X and verification key of X. But this certificate was generated by entity Y. So if you look into the entity Y, this guy also got a certificate called Y, which has been signed by somebody called Z on the top of this tree. And therefore, this guy has certificate of Y, signing key of Y, and also verification key of Y. So if you don't trust X, so you can see that who signed this guy, this certificate. So it says Y. So you go get the verification of Y to verify the signature on X, and X, then you see that whether this certificate is valid itself. And if it is the case, then you say that, okay, this guy signed this certificate is okay, so I don't trust X, so I use Y certificate to verify X, and then I get to Y, and it looked like that I run into this one on the very top on the list, and this guy has a certificate Z, so I'm going to use the certificate Z, verification key in Z to verify the certificate of this Y guy. So you see that this is a tedious step. You need to, go back on the tree until you reach to some point that we get to these special certificates. So Z, certificate of Z contains signing key or Z and also verification key for Z. And this kind of certificates are a special kind of certificate that we call them root CA. And these guys are self-signed certificate. So we start with the root. So the root certificate is something that when you install your operating system, let's say you install a fresh one, your operating system comes with some root certificates that you trust them by default. So this default certificates, of course, they are the root, so nobody else are on the top of them that they sign, their information. So they use their own secret key to sign their own certificate. So they are very special one. So when it does so, then there's no way that you can verify it, and that's why we call them root certificate. They are installed on your operating system by default, and then your operating system trusts these certificates. So there is no need to go on the top to verify this signature, signatures on the bottom of the certificate anymore. But now that you trust this guy, you can use this certificate because somebody comes with the certificate Y and it says that, hey, this certificate Z signed me, and then you can basically use the verification key for Z to verify whether the certificate of Y is valid or not. And then the X is claiming that certificate authority Y created the certificate for me. So again, you can go and use this verification key of Y to verify the validity of the certificate. And then over here, this user A says that, well, user X, certificate authority X created this certificate for me. Then you can go and use the verification key of X to verify the validity of the certificate for user A. So this is, how many calls you have to make. So we basically start all the time from the bottom. We get the certificate, we verify the certificate using verification of the certificate authority on the top, and then we use the one in the intermediate one to verify this X guy certificate, and then we most of the time we run into the root one to verify the validity of this intermediate certificate. At this moment, we say that, okay, we accept this user A's certificate, and we are able to communicate with them. So let me write this down for your future. So it was a lot of words. So 1, to verify certificate of A, so we obtain X and certificate of X, use verification key on certificate X to verify certificate of A. And 2, you're going to obtain verification key of Y and certificate of Y, use verification key of y to verify certificate of x. And 3, we are going to obtain verification of z, and this is going to be from the device. This is inside your OS. Use VZ to verify certificate of y, right? So we have completed this chain. By this 3 loops up, we are able to verify that, you know, certificate X is a valid certificate. All right. So now that we know that, in order to, you know, send a message to Alice every time that we want to do that, you know, sometimes we cache it, but in the beginning of the communication, we get the certificate of Alice and then the verification key of X, and then we verify the validity of the certificate A. We check the signature, we check if the start time and end time are not expired, and then if everything is okay, then we would start to send a message to Alice. We don't, you know, we never talked about this step before. We assumed that we would do that, but just in these 2 pages, I just wanted to make it clear that every time that we talk about, you know, encrypting a message and send it to some user, these are the preconditions that and pre-steps that we should do before we send that message to that user A, because we have to make sure that we are sending to the right user A, and, you know, that encryption key for that user is valid, and so on and so forth. All right, so I think now we get to start to discuss about something called identification schemes. Identification schemes are very interesting schemes, very interesting algorithms or protocols that we would be able to use them from now on, instead of that you know, normal username and password, you know, authentication system that most of the user and website would get to design. And you will see that these guys, these schemes would have very nice properties. So normally when you want to prove the identity or you want to authenticate somebody, you would be using some sort of PIN, some sort of password. You ask for a secret key, you know, or sometimes you can use their public key and ask them to sign some message, right? You can verify their identity, make sure that they are the person who claims to be. So today what we are trying to discuss is that these methods that you're using is a sort of interactive proof system. Interactive means that you're sending and receiving messages before, you know, a party or both parties convince that they are the ones that they are communicating to. So this is an interactive system, you know, because of that, and you're sending and receiving message for that. So let's start with our, you know, a small example. We always have a prover that we call the prover also Peggy or P, and this prover has some secret knowledge, call it secret key, SK. And then we always also have a verifier that we call it V, or we also denote it as V, that wants to verify whether the prover P owns that secret key. For example, the P prover can be a user Alice, and then V or verifier could be gmail.com. And whenever you want to utilize, you know, the services on Gmail, verifier, which is the gmail.com here, would want you to prove that you are indeed the valid user. That's why they ask you to enter your username and password, right? So that is the very basic way that you can do that. So we are talking about a general scheme now. We don't want to restrict ourselves to just that username and password scheme, but these are the 2 properties that we want this interactive proof system to have. And that is the case that if P knows the secret key, then this knows the secret, then Vic should accept, P's proof. And then the other property that we want is the schemes to achieve that. If V is convinced by P with a reasonable probability, then, P should know the secret, right? So you would see in some schemes that you don't have to send the secret key directly to prove yourself. You can do some computation with that secret key. Then again, you can prove that it is indeed me. So if I want to visualize this one, normally we have this prover that, we call it P or Peggy. And then we have this verifier that we always talk about, V or Vic. So verifier normally has a database of users and then the passwords, right? So she has Alice, and then maybe her password is Apple. You have Bob, the password is maybe password, the word password, and so on and so forth. So every time in a normal scheme, you see that Alice would send her username. It says that, hey, I'm Peggy, and my password is, and this is my password, pi. And so we check the tape when verifier gets this one. If we would check the table to see if Apple, if user and password exists, right? If so, then you can say that, okay, you were logged in. Otherwise, you can say that, login failed. But the problem with this scheme is obviously somebody like Eve can see this communication, right? So basically, the first time that you log into the system, Eve is sniffing the line, and of course, he would learn Peggy's password, and he would be able to log in from that moment on the behalf of Peggy. But before we start to discuss about the issues, so this completeness over here, so if the username and password are correct, so verifier would accept it, so we would pass the completeness. And then the soundness is that if Peggy is the soundness would also get verified, because when Peggy send her username and password to verifier, then the verifier will get convinced that this must be the verifier, because the prover Peggy, because she's the one who is supposed to know the password for this username. But I think let's continue, so we would see better cases that how we can do that. So I think here is what we are discussing. So the other problem that we haven't discussed is that sometimes it happens that with the previous scheme that sometimes the verifier itself get attacked, the content of that table would get leaked, and then there would be a serious issue over there, because you have heard on the news some years ago, for example, Yahoo's user table got attacked, and then they leaked the database, and then a lot of hackers got the username and password for many users, right? So there is another even attack over there that even supposing that you secure the communication, Eve cannot see it, but if Eve attacked the DB itself in the previous picture, Eve can go ahead and also attack this thing, and by the time that he obtains this username and password, then no matter what secure scheme you use over here to protect this issue over here, well, Eve already got access to this database. And with some examples in a real world scenario, we've seen that this is something that is, you can't say it is impossible. Right. So another way to discuss this is a solution is as following. What this scheme is saying is that let's use public key infrastructure to make this happen. So let me draw over here. So what it says is that the prover has a public key. So the prover has a public key and a secret key pair. And then so here is the verifier. So verifier, it says that the way that I can convince myself that this is indeed a prover is as following. I generate a message randomly from, let's say we are working on RSA from ZN, and I encrypt and send the ciphertext to prover. So encryption of, oh, I'm sorry, this should be consistent. So prover, and I send this challenge message. Basically, prover verifier would randomly choose a message, send it to the prover, and then the prover would decrypt this one, decrypt using the decryption key of prover of the ciphertext, and let's say he recovers M prime, and then he responds M prime, and then he checks whether M equals to or not to M prime that he received from Peggy. If this is the case, if M equals to M prime, that means that this is indeed the prover itself that was able to decrypt this message and send it to us. And the probability of that is high because the probability of M to be M prime is actually very small, 1 over 1 to the n, right? N is the number of elements we have in Zn. So if this prover doesn't know the secret key for this public key, then he would want to just guess what would be the message. So he would randomly send a message M prime to the verifier, and the probability for that M prime to be the correct decryption of the ciphertext C is just 1 over n. That is a very, very, very small chance probability for it to win. So basically, we pass the completeness, we pass the soundness, but there is a problem. What we are doing here is basically we are providing a decryption oracle, right? This is not a good idea because Eve can receive any ciphertext C prime that he wants to get it decrypted. He can play with prover and then get the prover to decrypt this one and send the corresponding message to the Eve, right? So what we are doing here is we are basically turning prover to a decryption oracle. So we know that the purpose of this algorithm for some verifier to choose a random message and encrypt it and send it to the prover to get it decrypted, but verifier doesn't have to be verifier. Some Eve can play the role of the verifier. Eve wants to get access to the plain text of this ciphertext or break this one. So then Eve would just play with the Peggy and pretend that I'm a verifier, and this is your challenge to solve. And then Peggy would decrypt it, and of course, Eve can recover all the encrypted messages that people would send to Peggy. So this is not such a good idea. Even though the algorithm works, things are fine, but we are causing another problem, and we are basically deploying a decryption oracle, which we are not supposed to do. So okay, we also failed there. How about another way? Is there any other way that we can do that? And the answer to that is a yes. So we would get back to this text. It looks a bit messy. Let's go and discuss it in our own way, and then we would go back to there. But essentially what we are trying to do is we are going to design another scheme that would help us to identify the user. But now we are going to use a discrete logarithm problem, right? So given that, you know, every user has a public key and a secret key. So let's go and see how we can design this system using the discrete logarithm algorithm. So we assume that there is a P and there is a G that is known to everybody, right? So these are the public parameters. So we form the group ZP with this, where discrete logarithm is hard in this group. That means that maybe the length of P is, maybe for today, is 1024 bit long, right? So we have our prover over here, and then we have our verifier. So the prover would start with generating a secret S, which is an integer randomly we take from ZP minus 1. The public key, public information, would become X, which is G to the S mod P. So now we can start to play the game. So remember that our goal is for the verifier to verify Peggy, that Peggy knows this secret key S over here. The only information that is available is this X, which is G to the S. So let's see how Peggy can prove that she owns this S without giving this S directly to the V. So we would start a prover would start to generate a random R randomly from ZP minus 1 again, and then compute and send A, which is equal to G to the R mod P. And then the verifier would choose a challenge C from randomly from the set 0 or 1. It would basically randomly choose a bit and then send that C to the prover. And then the prover computes and send B equals to R plus CS mod P minus 1. And then the verifier would choose, we will compute, make sure that if G to the B equals to X to the C multiplied to A mod P. And if this is the case, then verifier would get convinced that this is the prover. But let's see how does this work. First of all, let's confirm this step, if this step is correct. So let's start with the X. Let's say X to the C multiplied to A. Let's see what we get over here. We know that X itself is G to the S, and then we raise it to the power C multiplied to A, which A was G to the R times G to the R. And then this is going to be G to the power CS times G to the R, which is G to the power CS plus R, right? And this is going to be G to the power B. So correct. So it means that this verification is correct. So everything start from the beginning one more time. So everybody has access to this G and P. So every user would know that what is P, what is G, and prover has made some secret information for herself, and then she published a part of that secret public key of that, which is X, which is G to the S mod P. So this S is private, and this X is a public information. So imagine this is your username, X, and then S is your, password for that email. So every time that the verifier wants to prove that if this is the P, then the prover would start by sending some randomness, and then the verifier would send a challenge, and then the prover would use the knowledge of the secret information that no one knows but her, would do some computation. Over here, you see that she never sends S directly to the verifier. She used S to do some computation, so that at the end, the verifier would use those information that he obtained throughout this communication to verify whether that user is P or not, the prover or not. And the beautiful thing about this scheme is that we've never shared any value, any secret key directly. We never send X and S directly to the verifier. And of course, verifier can say that, oh, okay, G to the S equals to, X. So you are prover. But rather than that, we just use S to do some computation. And that was very interesting. So let's go back on the top. So now we've discussed this one, this protocol down there, and then we know how does this work. So the completeness is that P knows, S, which is the discrete logarithm of, X on base G. And then as long as he knows that some prover knows this S, then he can always, convince verifier on the above protocol, right? And this protocol would work. But another issue is that prover can always cheat with the probability of 50% of the time. So, and that has to do because we always choose a challenge. And if you can see over here, if the challenge is 0, so the challenge multiplied to the secret. So there are some times when the challenge is 0, you don't need to know the secret key to answer this to these challenges. You just need to know this value. And if that is the case and you hope for it, then you would be able to, some cheating prover can basically cheat with the probability of 50% to be a prover. So we can of course fix that one, but let's just focus on how can this cheating prover can achieve the goal. So from now on, we are going to denote P prime, or sometimes I'm also going to use P star as a dishonest prover. Okay. And let me give it a note so that this is our second discussion over here. All right, let's see how we can do that. So now we are looking into the communication between this P star and then the verifier. This is, it doesn't know without knowing S, right? So we are talking about a cheating prover or dishonest prover that doesn't even know the secret S, but he wants to convince V about that. So this is how this dishonest prover would work. The dishonest prover would start to guess what the challenge he would receive from the verifier. So he would randomly choose a C prime from 0 or 1, and then he would also randomly decide a value for B from Z P minus 1, and then he computes and sends A prime, which is G to the B prime divided by X to the Z prime. Send it to the verifier, and then wait for the verifier to return the C, the challenge, and if C equals to C prime, you know, the challenge that he guessed, and if he received the same beat from the verifier, then he would respond with B prime. And then the verifier would compute B prime, which is equals to X to the C prime, A prime, right? And then verifier would get convinced. Let's see why. So out of this computation, X was G to the S, C prime, and then we said that A equals to, according to this computation over here, is G to the power B prime divided by G to the power C prime X, right? Let me verify that. Right. And then C prime S, I'm sorry. And therefore, this whole thing would become G to the power B prime. So basically what we are trying to do is like we normally in a normal protocol, we compute A and then we receive a challenge, and then based on the A that based on the challenge that we receive and you know this randomness we choose over here, we compute B. But when we want to cheat, what we do is we guess what challenge we would receive from the verifier, and then we also set B to be a random variable, and then we compute A to be like this value. And if the challenge that we receive is correct and we made a correct guess and is exactly what we were looking for, we can just send this value B prime, because we know that we have crafted this A so that we can pass this equality over here. And if this is the case, then you know we can return it and we can win. Otherwise, we can abort. Because if the challenge that we receive is different from what we guess, then there's no point to send this B prime, because of course B prime V would catch us and say that, I know that you're not a correct prover, you're cheating. So if that is the case, we could just abort and we don't have to continue the computation. So this is a problem. So it looked like that we have our scheme and everything is fine. The only problem is that based on this design, there is a 50% of chance that the verifier can basically the prover can cheat. We can fix this one. There's no problem. We can imagine that we can run this many times, and you know, maybe you cheat one times, you win. You cheat twice, you win. But when we run this for T times, there is a very likelihood that you make a wrong guess for C, and then you basically lose in one of those rounds, and then the verifier would be able to catch you. I think the next thing that we want to discuss about it is that from the security perspective, that the prover can only cheat with the probability of 50%, but he cannot cheat with probability of more than 50%. So that is something that we are going to give a security proof right after your break time. So I think we can have some break time and then come back at 10 o'clock to continue our class.